Just quickly recap. We've gone through the whole music classification stuff, but mainly just talking very high level about it. It's related to a lot of, downstream tasks. That's why, we oftentimes need to think about why we are doing music classification. So likely the most relevant stuff is about, your streaming platform, how you do the playlist, how do you get the next song. So having a lot of, more metadata about the songs that would help definitely help how you generate the playlist. And nowadays, last 2 weeks ago, Spotify just announced that now ChatGPT can you can ask ChatGPT to generate Spotify playlist. So we are entering sort of like the next year era of music recommendation. Um, um, you know, um, Era of next generation music recommendation, basically, where you can sort of like conversationally talk with your streaming platform. That's interesting because, think about when you're driving, it's not like play the next song. It's about, well, can you sort of like turn that into something else? So it's more like a conversational interface to see how you do the playlisting. Um, Cool. So these are likely just more details about the classification. But mainly we talk about this accuracy thing that doesn't really work in a lot of scenarios, especially when you have an imbalanced data. By imbalanced data, meaning that, you have, um, very 99% of the time, think about like a binary classification for a very niche genre, then 99% of the time you are predicting no in that case. So accuracy is not a very effective measure in that case. So we have to look at precision and recall. So precision is how often predictions for the positive are correct. So you can think about, this is like you care about all the predictions. You want to see how many percentage of those are correct. And recall is another way, is like how well the model finds a positive incidence in the data set. So this has like implication. So, in precision, you look at false alarms. In recall, you look at misdetection. So, in certain scenario like rare cancer detection, then you'd probably care more about, missed um, detection rather than false alarms. So in that case, you might be looking into, a high recall so that it ensures most cancer cases are identified. But on the other hand, if you're just thinking about, the immediate next song in your, recommendation algorithm, then likely you don't really need to care about whether you cover all the possible songs that you want to recommend. It's fine, right? So you look at the precision about, what are the rates of, correct predictions in the next few, predictions. So you care more about false alarms than misrecommendation, because in this case, misrecommendation, if it happens later, it's fine, right? Because the user likely only care about the next song, the next song, the next song until when they want to switch to another sort of like radio. So this is when precision and recall has to depend on your particular use case. There's also other measure that just sort of like blend these two things. F1 score. There's actually also F0.5 score, F2 score. So that one is sort of like doing a weighted sum between precision and recall. But another very useful thing that we will explore in PA4 is confusion metrics, but basically looking at, how the model are making mistakes. And by looking at how these models making mistakes, you actually learn something about whether the model is doing something, reasonable. So, bass sounds got classified as keyboard sounds. That sounds fine because, keyboard with like very bassy sounds will sound more like bass, and bass and guitar can be confusing to detect. So, the models sort of meaning that it's doing something reasonable. So yeah, this is essentially what we want to get from PA4. It's still flashing again. Um, and there's additional slides in the slide deck, but I won't go over it. But it's basically talking about all the optimizer stuff that we might be using in PA4. Cool. So PA4 basically shouldn't be too tricky. It's just training a model, but sort of like the code is provided. So you basically just run it through again, and you will realize that most of the time you will be working with doing with the data. So the data can be found here, just following the step. These are if you are doing it on Google Colab. And these are instructions for doing it on Great Lakes. Great Lakes has the benefit of, keeping the data still there in your home directory so that you don't need to worry about it. But Google Colab is much easier to set it up. So up to you. The file can be found in this Google folder, so you can download it, add it to your Google Drive, and you can actually mount your Google Drive to Google Colab so that it won't just got cleared every time you rerun Google Colab. So likely just follow these instructions, then you can get the data set up. I've already pre-processed the data set, so it shouldn't be an issue. That's usually the most time-consuming step, but anyway. Pre-processing. Okay, I don't know what's going on. There should be this page. Let me see if last year's one. Hmm. Hmm. Yeah, here it is. So this is how I do process the data. So this data set is like NSYNC. But basically what we want to do is load every waveform, Liberosa load, and then we compute the male spectrogram. So this is like Liberosa, the feature the male spectrogram, so that you have the waveform and you set the sampling rate. In this case, we are setting like only 8,000 hertz, which is fine in our case, because what we want is just 64 by 64. And think about 64 by 64 is very low resolution actually. But this make our CNN much smaller. So M males is like the frequency range, and F max set the highest frequency. So why is that 4,000? Any thoughts? Because the sampling is 8,000. So that's technically the highest hertz, like the frequency that we can detect, right? That's exactly the sampling theorem is talking about. Like we can only detect half of the sampling rate that we can have. So sampling 8,000, so you set F max to 4,000. So this is because when you're doing male spectrogram, you are sort of remapping the frequency range. So if you just do SDFD, it would just do, sort of like 0 to 4,000. But in this case, if you want to map it, it's actually redefining 0 to 4,000 into this male range where it's log and sort of match our human hearing range. So male spectrogram is actually more commonly used in speech processing, where speech is very constrained in the pitch range. It's usually, this and, 1 octave above and 1 octave lower. So FFT and SDFD is actually wasting a lot of like frequency range because we don't really have those, very low frequency components and high frequency component. So male spectrogram is basically remapping the scale of frequency. So this is the male frequency range. So you can think about it something like this. Oops. But basically, you're remapping the frequency. So each of these male beat correspond to a frequency range. So, you can see that in lower frequency, it's much smaller, but in higher frequency, it's much larger. So, because, somewhere around 3,000 hertz and above, it's like we don't really care a lot, especially in in speech processing or in music processing. Something very high beyond it's not that important. So we lower the resolution by collapsing, aggregating those frequency bin into one. Um, so yeah, that's what Mail spectrogram is doing. So it's just the same spectrogram with the frequency range remap to 64 bins. And we have to change it to dB because otherwise, if you look at the original spectrogram that you get, it's like too high contrast. You couldn't really see what are the texture. So we turn it into decibel. And we have to normalize it. This is like decibel, so it's a little bit tricky. So I set the minimum to be -80, maximum will be 0, and I have to remap it to 0 to 1. That's basically what's going on. And this is to see if the Mail spectrogram is smaller than 64 by 64. Sometimes it's only 3 seconds. Then you have to pad 0 for those. But anyway, at the end, you will get a bunch of Mail spectrogram that's 164, 64. And that's essentially the main script. Everything else is just doing parallel computation. So these is just doing parallel. You can see that it takes 30 minutes to process this data set for 300K files for the training set. If I use like 20 jobs, so it takes 30 minutes. So if you don't do parallelization, it will take I don't know, times 20, 10 hours. So yeah, everything else is just doing this thing. So joblib is the parallelization thing, much easier to use. Um, cool. Anyway, once you've done that, I mean, I've already done that, then we will get basically these folks. So these are the process one. So 64 by 64. So you can see the y-axis is like remapped to different frequency range. And the y-axis is a very low resolution. But still, I mean, 64 by 64, you can still see their corresponding textures. Um, cool. Anyway, other than that, it's just training a CNN model to do the classification. The file, the Google Colab stuff should be self-explained. Most of the time, likely you will be messing around with the data set. The model itself is just, very standard CNN. You can see, oh, I actually have a lot of stuff. So this is our data. So, once you unzip it, it could be just a bunch of file, trend, mail spec, and blah, 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 dot MPY. So you can actually just load it. I already save it as MPY file. So this is essentially what you get from your data set. So this is a 64 by 64, but we plot it into like using the Barossa. So it doesn't really look like a square, but it's technically a square. This is what it sounds like. I don't think there will be sound because I didn't connect. Um, yeah, but basically you will be looking at different. Well, that's it. Guitar. There's a bunch of other sounds. Guitar, this one, bass. Um, Basically, you will just want to predict the class, and the classes here. There are 11 classes. You can find it somewhere here. These are the classes. So basically, you just want to predict those. Um, cool. So this will be the convolutional network that we are building. But likely, we can likely what's going on. So and then that conv2D to define the convolutional neural network, and we will go through like a max pooling layer. So these are like lowering the resolution, but also um, passing through a bunch of convolutional neural network. But you will have like max pooling to reduce the resolution by half. There's also some dropout that we didn't really talk about, but it's just like adding more robustness to the model. And finally, we will map everything that we got from the data, from the neural network output and map it to the 11 classes that we have. So n classes here is 11. So at the end, it will be just like a vector of 11 classes. Other than that, just run the model, you will see how it goes. We will train the model, and this is the main training script. It's huge, but you will see how it works. And it should plot after every epoch about the training and validation loss. So basically you just run it and see whether it works as expected. And there is additional questions that you have to go through the test set to get the test results. Um, yep, pretty much that's it. Have you trained something CNN likely in another class?
I haven't made my own yet. We have a project.
Okay, cool. Yeah, this should be much easier because you're technically just running these files. But it's fine. Just looking through it. This should be hopefully good implementation in PyTorch. So just to get yourself familiar with these stuff. Yeah, cool. Um, it should take more than trivial time than the other assignment. This should be the most tricky one. It will be due November 3rd, so 1.5 week. Cool. Um, cool. And other than that, there's just some additional slides that we can talk about it, but likely after when we have time, I guess. Cool. So today, I guess we should jump into another big chunk of the course is about generation. So let me grab the slides. So this is likely when you think about music and AI, what people are expecting. So nowadays, people are doing a lot of like generative stuff rather than doing the traditional music you know, um, analysis or, more processing, analytic side of stuff. Oh, and we should talk about the project. Anyway, we will have the project pitch 2 weeks later, open-ended. There are several milestones. The pitch will be on November 5th, so 2 weeks later on Wednesday. Yeah, I will send an email so that everybody are aware of this. Um, and the presentation will be December 1st. I will be traveling the last week of the semester for a conference. So we won't have class then. So presentation will be a week before. So that will be a week before the final week, December 1st. The report will be due, after the whole final exam, so December 15th. I think that's technically the last day I can do it. Anyway, so yeah, same, submit it as early as possible, and you can update it, and I will start grading after December 15 anyway. The topics should be any of these. You can build a new AI music tool if you like. It will be a little bit challenging, but it will be fun. And it doesn't have to be, completely novel. It could be, integrating different components, different existing models, or try a new pipeline to do something interesting. You could also explore, creative or artistic use of AI tools. So it doesn't have to be, very technical. It could also be, creative focus. The last one is also cool. Analyze systematically existing AI music tools. Some of the ideas will be, looking into how the genre coverage, or does these model actually work for most these model are biased toward Western music. So what are the limitations? What are the goods and bads of these things? And last semester, there's also a group working on a very interesting case. It's about AI Turing test. And they figured out that, mastering, AI mastering is doing really well. If you are not trained well enough, there's a high chance that you couldn't tell what between, human master output versus, AI mastering outputs. So these kind of an analysis is very interesting to see, what's the limitation, or, what has sort of like blurry blur the line between, human and AI. Here are the rubrics, but likely will be very easy to get all the points if you did it right. Should be very easy to get those. The project pitch will be just brief 10 minutes presentation. The topic, what do you want to work on? Who are your target audience, users, customers, and readers? I think this is very important, especially when you think about this topic, and also when you're doing research, it's about, thinking about what exactly you're doing rather than, well, I just want to build this because this is cool. So think about who are the potential, you know, target users that might be using whatever you are building, then that will better shape the goals and the focus of your project. What are your goals? Methodology, how are you going to approach it? This is pitch, so likely it will be very high level. What are some of the tools so that you get a sense what you are expecting, and you can also, by thinking through it, you can sort of like rescope what you want to do. Expected results, of course, you don't know what would that be, but what's kind of the format of that? Are you building an instrument? Are you building a plugin? Are you building a web mobile app? Are you building a standalone software? Are you building an installation? Is it a performance or composition? What would be the expected results? And like a rough timeline and milestones, even though likely challenging to follow it. Just on project should be fun. Technically, we could do 1, 2, 3 as a group, so we can technically have one group only. But I guess it's up to you if you want to join as a group, or individual is also fine. So totally up to you. And you can book the office hour if you want to chat, or just let me know. I think the office hour is only Tuesday and Thursday, 2 to 3, but let me know if you want to chat. There's other times we could arrange. Cool. Yeah, and I think we can start with AI song contest. So before we jump into the generation part, I just want to talk about this very cool AI song contest. So this will also be our second last homework. So homework will be much easier. We just go hop on this AI song context and listen to some of this song to see what's the state of AI and human co-creation. So this is like AI song contest. So apparently this year will be at Amsterdam, which is cool. But this is like annual since 2020, I think. So this will be the sixth likely. So, people will submit their work and write about how they create these songs. And now I think it's already the final round. So if we are running a class in fall, then we will get to experience this. You can actually just vote for those. So it will be 50% by the jury, and 50% by the public votes. So these are the the finalists. We could, data bots.
I fuck you up, motherfuck you up. I fuck you up, yeah.
Okay, that's Databots. So Databots is a very cool team actually. They've actually launched a very cool like YouTube channel with like never-ending metal songs, and at some point they actually got I think like some interruption on YouTube. Otherwise, it's super long, like it's never ending YouTube channel. You can find it somewhere on Dadabut's channel likely. I don't know how long that is. Yeah. Like this is like 4 hours. Anyway, so part of the homework will be just like listen to all these songs and read about what they actually write about those. So you can actually click the cover art to see how they do this, especially about the human AI process, how they work with the AI to create the songs. This team also won one of the previous competition, I guess. Anyway, that would be the second last homework. So anyway, I think we could look into some of the past winners. So this is one of my favorite song actually for AI generation. So let's give it a listen. Not this one.
Hey, it's your boy Hanoi, and this is how to make AI-based music from
this one. No, this one. Yeah, this one. It's actually playing through like traditional instrument, a lute basically, a flute or a pipe. But they are using saxophone to sort of use this tone and everything to grab the pitch and grab the pipe flute and you try to map it back to so we can actually look at how he created this, which is very cool. This one, I think I've opened it up somewhere. Where it is, this one.
From Thailand. Instead of using symbolic AI to model music as notes, we can use audio AI to model music as frequencies. Audio AI can precisely analyze melodies from the B-night in hertz. AI tools like Morph can re-render the precise pitch information from the B-night into the sound of other instruments.
That's the bad stuff. What you just saw is it has like a specific view system, so we cannot actually use symbolic, music models to model that. So you cannot actually transcribe it into Western notation. So what they are doing, we will talk about it next class. It's about a model that's sort of similar to differentiable DSP. So that's the model DDSP, so that you can actually transfer the tone without transcribing it into like Western music notation. That's, the way how we do synthesizers. But this way is that audio to audio directly doing that timbre transfer. So nowadays, AI models can do all sort of these kind of things where you could, Hanoi is very interesting in this because this way you can actually make it extend beyond the traditional, Western notation, so that, there are other, cultural heritage where there are specific tuning system that cannot be easily, mapped to Western music notation. And by using these Western music notation models, we are sort of like imposing these, hidden biases into the model that we couldn't extend it beyond that. So it's very interesting. So, because, you can do some transcultural ensemble where you have the Thai motifs, but now played in different, instruments that we might be more familiar with, but at the same time, it still have that Panay tunings. So that's actually the winner of 2022. So I actually vote for him. So it's really nice that year. I think that's the third version of AI song contest. So this is like the 2023 winner, which is also cool. Because they try to use so 2023. I mean, just looking at all the past iterations, you can sort of see how music AI evolve over time. So in the past, it's like we couldn't really do everything with AI alone, but nowadays, more and more AI tools coming up, we can actually make it even more AI. But at some point, then we will revert it back to think about, then if everything is AI, what's the point of having human, in the process? So now we are starting to think about it again. Now, a lot of things can be done with AI, but now it's time to rethink about then what's the value that we are adding, and how should we interact or, partner with the AI systems. So this is one of the no, this is the winner in 2023. So you can also see that the visual is also cool. This is using the control net. This is like an image generation model where you can say
I was created
you
to
dance or you are doing
love,
some gesture, you
but
do
could never
skeleton
feel like a
analysis on
human
yourself, and then you
does.
can impose it onto a specific prompt.
My circuits process, data they churn for the warmth of true
These are like
love. I
dance,
deeply yearn.
when someone dancing,
Cannot
that
be
you can do
between
skeleton
us.
analysis and use
Or
control
is it
net to
just an
generate
illusion?
the image. So you can actually use like stable diffusion like model to do it. So likely on Midjourney, you can do something like that. So this is interesting. If you want to give it a listen, then, you can also read the longer file that talk about the whole process. It's a much longer file than other submission, but they basically talk about how they actually use all the AI tools to do it, from ideation, just looking at, what are the popular songs, how can we rewrite these lyrics using, existing LLMs, think about the lyrics, and then do the composition. There are so many models they are using at the same time. They also, synthesize the vocals using AI models. Mastering is also done using AI. They also generate the cover art, the thing that you just saw with Midjourney. And, so I mean, each of these, winner is very interesting because, in this case, they are just exploring, can we sort of like use AI for every step of the production process? So, all the way from the very beginning, what should we write about, to how can we refine the lyrics? How can we write, get the composition and each single different parts. You have like drum machine. This patch does not exist. It's like a very interesting, website. And IVA, MuseNet, those are symbolic music generator. But you have different tracks, but you can use different composition tools to do all the tracks. And you can synthesize the singing voice, in a lot of different platforms, mastering to cover art and clip. And this is like the last year's winner, Santa Marica. I should play it on YouTube.
Sudamérica, tierra de pasión, fútbol en las venas, samba en el corazón. Sudamérica, Andes majestuosos, selva sin igual, un sueño tropical del Caribe al cono sur, la diversidad
one of the very cool things about this song is that they actually sort of like did a very
incas, mayas,
guaraníes,
su historia prevalece en cada rincón, la tradición se estremece. Selva amazónica, pulmón del planeta, cordillera andina, majestuosa silueta, lenguas que perduran, culturas que se unen en esta tierra donde los sueños se reúnen.
Understand what the
Tierra de pasión, fútbol en las venas, samba en el corazón.
So this is sort of like how they started this work. It's about, just prompting and, talking with ChatGPT, Cloud, and Gemini, and, think about, what's your understanding of our culture? What's your understanding of this particular region? And grab those, concepts and get those keywords. So this is a very interesting process where you look at, ChatGPT or Cloud and Gemini sort of like capture the joint understanding of at least the web appearance, where people, because these models are trained with all the web text. But they also do a lot of different things. They also try to keep all these components into 5 seconds, 5 to 10 second base, smaller chunk of motifs and things so that they can rearrange. But anyway, at the end, they also do lyrics to use Cloud.ai, and they also use Moestis.ai to separate the music that they get, and Kids.ai to finally do the vocal. Anyway, the homework would be looking into all these 10 entries. The finalists of AI song context shouldn't take a lot of time. I mean, at least half an hour, I guess. If you want to read through, listen through all the files, all the songs. So just listen to it, but more importantly, click on the cover art so that you read about the process, and vote for it, and then think about what's the state of AI song context. What's the state of people exploring the human AI co-creativity. So this is actually back in 2020. So that's the first time they're running this AI song context. And, they did this, they wrote the paper about it to see what are the different groups. So at the x-axis is the teams. So these are the certain teams that are using it. And you have like different legend. It's like purely human, some human, some AI, just AI mostly. So you can see, lyrics, melody, vocal synthesis are AI is helpful back then, 2020, because, you can sort of see the progress of how AI go. And nowadays, structure and arrangement, instrument synthesis is still very not there yet. These AI couldn't really help. AI can be helpful in harmony, bassline, and percussion. And nowadays, likely, it's doing much better. So, this is the first AI song context in 2020. Anyway, other than that, just take a listen on all the 10 finalists. And it's also interesting, if you want, you can go back in time to see, the first AI song contest, and you will realize how different they sound, in the past and nowadays. And all these teams have different ideas that they want to explore. Cool. Shouldn't take a lot of time. So the instruction is already on the website. Cool. Questions on that? Nope. Yeah, so in the next few class, we will basically talk about music generation. So the first thing, like you've seen in Hanoi's explanation, that there are like two sort of big paradigms of music generation. One is on symbolic side, where you are just doing symbolic music generation. We sort of like hinted a little bit when we talk about how you represent music as like symbolic way. So MIDI is likely the most iconic way to do it. Then you can sort of like use ChatGPT or use ChatGPT like model to generate music in MIDI format. Image-based piano roll, we can actually just treat these piano roll representation as image and sort of like try to use some of the image generation model to generate those. That's what we will talk about next week. Time series for audio. So audio is a little bit different from symbolic, where audio is expressive by nature, and you are working with raw data, basically. But image-based model can also be applicable here, spectrogram. So nowadays, most of the big, like think about Suno, Udio, think about Moises, like AI Studio. These models are actually based on sort of similar to spectrogram-based models, but sometimes they are also waveform-based model. And that's essentially the latent space-based models that we will talk about at the end. That's sort of like a merge, a blend of everything. And that's essentially what nowadays, Musical Lamp, Audio Lamp, Suno, all the different music FX, all the different models are many using. But we will start with symbolic music generation. So there's a bunch of topics of symbolic music generation. We will mostly focusing on, unconditional generation. If you want to learn more about other things, there's another class I will be teaching next semester is like more details into the music generation part. But in this class, we have only 3 to 4 weeks on music generation, so we won't jump into other case. But unconditional generation basically meaning that you're just generating something from scratch without any inputs. So empty sap to melody, lead sheet or sheet music. So lead sheet is basically melody plus chords. That's one of the most commonly way, especially in jazz culture. There's also conditional music generation. You can think about arrangement. So, from melody to lead sheet, basically you are predicting the chord progressions for the melody. Or you want to rearrange a melody to a multi-track, or, think about lead sheet is just melody plus the chords. Can you realize it into a real composition rather than just melody and the chords? And you could also do solo to multi-track, multi-track to simple version. That's also interesting because this is like basically reduction. Or, think about, in department of conducting, when you are, practicing for an orchestra, oftentimes you need to, play it on the piano. So that's essentially piano reduction for orchestral pieces. There's also performance rendering where you'd want to do, borrowing sheet music into expressive performance. There's also improvisational systems where basically you get real-time input, but you want real-time outputs at the same time. And nowadays, there's more interestingly a lot of like multimodal models, text to music, video to music, gestures and motion to music, brainwaves to music, sort of like anything to music. So this is one of the things that I'm currently working a lot on my research side. So think about video to music. That's very interesting because I'm very interested in movies. So think about film scoring. That's essentially very hard. Much harder than just generating music from scratch because you have to sort of understand what's going on in the video to see what are the connection between what you see and what you hear. Gesture and emotion is another thing that I'm very excited about. It's like, can you use your hands or, use your body movement to control these music generation system rather than, having them just run by themselves. So some of the ongoing things I'm in my lab is just doing this gesture and motion things. I'm thinking about, like conductors conducting the music, but can we sort of like conducting an AI orchestra that will, generate music on the fly. So, gestures and motion, how those connect to music, it's very exciting. There's also some, interesting research going on brain waves to music. It sounds crazy. We will see in the end like an example of that. But you can actually record the EEG of human brains and while they are listening to music. And the goal is try to sort of like reconstruct what the music is. And, people have shown that if you have like good enough, fMRI scan, or, EEG, you can actually sort of recover some of the chords and the timbre of the music, which is pretty cool. So, in the future, there could be, a brain interface for music generation. That would be super cool. Anyway, we will be talking about a lot of the extensions. So we will focus on the core, the most fundamental part of it. There are like two paradigms, as I said. So text one, we sort of like explore it a little bit, but we will talk about it more. There's also the image-based one. So basically the text one is like treating music like language or text. So we share the models with natural language processing. So think about RNNs, recurrent neural networks, long shortened memories, LSTMs, GRUs, transformers, etc. But basically, treating music into text-like sequences. Image-based one is treating music like images. So those are like piano roll representation mostly, but there are also some, other representation like tonettes and, other way to represent music. But basically you can share models with CV and CG because computer vision and computer graphics. So like GNs, scans, generated adversarial networks, variation autoencoders, VAEs, diffusion models, of course. But these are the two paradigms. So we would talk about the text one. We already talked a little about it. So these are mostly recap. So we talk about ChatGPT basically just doing this like word by word generation. And we talk about this is basically a language models where a language model is just trying to predict the next word given the past sequence of words. So, you think about a transformer is blah, blah, blah. And that thing could be all different kinds of possibilities, right? So, some of these make sense, some of these doesn't make sense. So, a transformer is likely not a type of food or a musical instrument. So that's essentially what these language models want to model to see what would be the next word probability given all the past words. So this, mathematically is just the, the probability of the next word given the previous words. So think about this way is that, a transformer is there, then this next word could be other different words. What are the probability of getting those? And that's essentially the same as the music language models. So now rather than predicting the next word, now we are predicting the next note. So, you have all the previous notes. You want to predict what the immediate next note is. So in this case, CCGGAA, we keep using this example is like the basically Twinkle Twinkle Little Star. So what will be the next note? So I'm just making this up, but these notes could be more likely than A sharp and A flat. So basically, these are the music language models that we would try to learn. And once you get these language models, what's the next word probability, then you can actually just generate a new sentence using the trained language model. So imagine this is the case where your model will just predict what the next word is over the time. Of course, if you just use the greedy algorithm where you just pick the most likely word, it doesn't really work because you think about a transformer is then what would be the next one? It could be something very generic, so like a concept that is interesting, things like that. It doesn't actually introduce anything. It's just writing about something very generic. So we have oftentimes need to think about the randomness. We want to get those lower probable words with lower probability, but with more meaning with those. So there's some randomness involved, and that's called sampling. But anyway, we won't go into those details, but basically you want to know what the probability of these words are, and you try to introduce and work with those randomness so that your model can be generating something fun. Cool. So the biggest challenge in the whole symbolic music modeling, especially when we are treating them as text, is how can we represent music in a way that machines understands. Cool. So I guess we're still sort of like recapping stuff because this is basically, we've gone through it a little bit. We've went through it a little bit. So the ABC notation, we look at it. So basically, you know, representing music as like just letters, alphabets. So in this case, C, C, G, G, A, A, G2. So by default, there will be quarter notes like this, like quarter notes here. When you have two, meaning that double the duration. So this is like ABC notation. So this is actually the first model that we can look into. So it's like back in 2015. We can actually play with it. It's only doing folk tunes because folk tunes, you actually have a data set, like a website, people submit their ABC notation onto that, and they basically just train it with 24K folk tunes, and they're using ABC notation basically. We can play with it. The website is called thesession.org. Anyway, let's do something. C major, random C. Compose. So you can see that it's actually generating on the fly. The RNN. So you have like meter 4/4 C major. Let's see how it works. Not bad. So you can actually also change the keys. Let's do C Dorian, I guess. So this will be, because these are folk tunes, so they actually have you know, other upscale. Anyway, that's sort of the first thing we've tried as a field. So folk RNN is like 2015, sort of like one of the very first model that people are generating music using deep learning. There's actually other work that's like, I think the first one is by LSTM, much earlier, like 2008, I guess, generating, you know, jazz, you know, melody plus chords. But folk RNN is sort of like one of the early, you know, more than models that we are looking into. So these models are using a kind of neural network that we didn't actually talk about it yet. So these models are recurrent neural network. So nowadays people are mostly using transformers. So fewer people are talking about recurrent neural network. But still, that's, you know, before transformers, what everybody is using. And it actually still have some benefits of, you know, having a much smaller memory footprint. So transformer is known for its good performance, but at the same time, it requires a huge amount of memory because of the attention metrics that we will also look into later. But, you know, RNN is just a model that's very efficient, actually. So these are type of neural networks that have loops. So by using loops, you can sort of like reusing the same models again and again and again to do these sequential modeling. So think about how you want to generate the next word. Then you basically want to have the previous several words to generate the next word. But can you just repeat this process by using the same model to generate the next word? And then by generating the next word, you still look at the previous words immediately. So if you look at what RNNs look like, it's basically look like this. You have some X inputs into the model, and this model will output something. But at the same time, this model will send its previous output back to its own. So you are keeping track of the previous data. So you can look at it sort of like unroll it into something like this. So this is like the first inputs that you put into the model. So X0, so now there's nothing coming in, and you generate something that's like H0. In this case, think about it's just like one single layer. Then it could be Y0, that will be the immediate output. But at the same time, this H0 will also be passed to the next one. So now you are using the previous H0, combine it with X1 to generate the next prediction. So, think about something like this, and RNN put here, and then RNN is, and then you get the is, and then put it here to predict the so you generate each word sequentially. And the key of these RNN is that there's some memory going on in the middle of these models. So that's essentially what RNN is doing. You want to have some memory or understanding of states in your model. And here we are using A as capturing the whole model, but this model could be very, very complex. Cool. So the core of our RNN is just combining the memory and the inputs to make the prediction. That's the key. So, the simplest form of biome is just look like this. Basically, you would just do the traditional way. But anyway, you could actually unroll it. But, a lot of like matrix computation, but still is just doing some calculation. And if you want to train these kind of model, you sort of have to think about it just like these RNN is just essentially a very deep neural network where all the layers are just the same across time. So essentially what you are trying to do is just, you can actually break them down into something like this. Cool. So that's RNN, but I guess we can jump into what's LCM now. So folk RNN is not actually using the traditional RNN, it's actually using this LCM. So have you seen this? Yeah, so I guess one thing about LSTM is that if you stare at it, it's still unsure what's going on. There's a lot of stuff going on. So I mean, we won't go into details of what LSTM is, but the high level ideas it's sometimes very confusing to look at it. So one thing about LSTM is that there's this long-term memory module that's different from the traditional RNNs, where you sort of have a highway of memory. That memory thing is the key of what we call long-term memory. So LSTM is long short-term memories. So you have long-term memories, you have short-term memories. So the long-term memories is the key of LSTMs. So the first thing you want to see is that whether we want to erase the stored memory. So this is sigmoid. So as we talk about, sigmoid is like a switch, kind of like 0 to 1. So you want to have a switch. So you have some input X. You want to see, based on this input X, you go through some sigmoid to determine whether we want to update the input. So, if this is like a 0, then you will erase everything. If it's a 1, we just keep it. So that's the idea. So it could be 0 to erase everything. It could be 1 to keep it. And the second thing is update the memory. So now still you have some inputs. Now you want to see how much information you want to add it to that memory. So look at the final one is the plus sign. So you are actually grabbing something and see if you want to update the memory. So the first thing you want to see is that should we remove the whole memory? And the second thing about, if we remove it or if we don't remove it, anyway, do we want to update the memory? So now you are doing something here. So it will go through something, so compute something, but that something will be added to your memory. So first you determine whether you want to erase the stored memory. Second thing, you want to see whether you want to update the memory based on your inputs. And finally, you basically want to combine the memory and the input to make the prediction. So you will see here that there's something going from the long-term memory, going through tangent, a hyperbolic tangent, times it with the input through some gate, and together get the output. So this output is combining the memory and the input to make the actual prediction. And then the things will be sent to the next input. So that's essentially what LSTM is doing. They have actually their own names, but it's always sometimes very tricky to see. So cell state is the long-term memory we are talking about. For gate is essentially what we talk about. Should we erase the memory? And we have input gate to see how you turn the inputs to control whether how much information you want to add it to the memory. And you have the output gate to see, how you combine the memory and the inputs together to get the output. Cool. Anyway, we won't go into the details about LSTMs, but I guess the high level idea is that this is a very interesting mechanism, back in 1997, before all the, more than deep learning stuff is going on. But basically, can we sort of like maintain a memory within the deep neural network where you have all these gates to control how you store, erase, and update the memory. They also have benefits of, alleviating this managed gradient things, because, gradients will be smaller when you are deeper neural network. And by having these LSTM, there's actually this highway on the top. So it's much easier to do the stuff. So, if you look at the gradients, if you go through this highway, it's very strong. If you go through these or the computation, the gradients will be much smaller. So by gradient is meaning that the inference from your inputs to the outputs. So LSTM allow you to have those highway connection. But it does not completely solve the vanishing gradient stuff. Anyway, so that's LSTM versus RNNs. So basically, it's a much complex. There's an improved memory module, better long-term memory, easier to train in general. So RNN is known to be very hard to train. Anyway, this is like folk RNN that you can actually use LSTM to generate music in ABC notation. So sort of similar to ChatGPT can generate ABC notation, just that we are using more earlier model that's LSTM rather than transformers. Cool. I guess that's what we can do today. PA4 and homework 3 is up. So